Year 11, homework 10. We've got one of these summary tables again. Again, I don't think you're ever going to get a table like this in the exam to fill in, but there's lots and lots of information here that's needed to fill this in table that's pulled from all different parts of the specification. I'll try and point out where from as we go through it. You will, however, be asked many times to write balanced equations, so a great exercise to do. First one, hydrochloric acid reacting with calcium carbonate. This comes from the year 10 module on neutralisation. Okay, neutralisation, acids react with either metal oxides, metal hydroxides, or in this case, a metal carbonate. And they make a salt plus water plus carbon dioxide. So you've got your hydrochloric acid, your formula for that is HCl, I'll give you that one. Okay, you've got your calcium carbonate, your formula for that is CaCO3. So those two are going to react together. And they're going to make calcium chloride. Okay, that is the salt. The formula of calcium chloride, I'll be generous just because we're at the beginning of this and give you that formula as well. When they react together, they're going to make calcium chloride, okay, CaCl2, and water, and carbon dioxide. I've said the reaction type is neutralisation, so I want a simple equation for that. Just to help you, I'll give you an equation for magnesium. What should we do? Magnesium, I'll give you an equation for magnesium hydroxide. Okay, because that's an alkali, metal hydroxide. That will react with nitric acid, HNO3. Okay, and that makes magnesium nitrate. And water. Okay, now, so that's a simple equation for that one. This one down here, this is going to give off carbon dioxide as well, because you're starting with a carbonate. Okay, just remember you need to balance it. So count the number of atoms on the left and the right and make them equal. One magnesium there, that's okay. You've got two oxygens inside those brackets there. Okay, but we've got just the one over there. I know we've got oxygens here in this nitrate as well, but we're going to take that as the nitrate ion. So we've got two oxygens here. So I'm going to put a big 2 before that oxygen in that water there. Okay, so I've got my 2 hydrogens inside this bracket, and I've got 1 hydrogen here in my nitric acid. So we've got 3 hydrogens on the left. I've got 2 times 2 is 4 on the right. So I think I'm going to need to put a 2 before that, the nitric acid as well, to get my hydrogens up. So I've got 2 hydrogens there and 2 hydrogens there. So that balances the hydrogen. I've now got this nitrate ion here. We can deal with this together. So there's 2 nitrate ions, and here I've got 2 nitrate ions. So those big 2's balance that equation. I want a balanced simple equation down here. It looks a bit like that, but for that reaction. Sodium iodide reacting with chlorine. So this is the start of year 11. We did a module on the periodic table and we looked at the halogen group. This is the displacement reactions of halogens. Okay, I'm going to do a different one. I'm going to do, say, potassium chloride. What shall I do? I'm going to do, I'll do potassium bromide. I'll do potassium bromide. Okay. Reacting with fluorine and fluorine. Okay. Now, what you need to do when doing these is think about the order of reactivity, because in displacement reactions, the most reactive halogen is going to take the cation. The cation is the potassium. Okay. Now, the order of reactivity is fluorine, chlorine, bromine, iodine. Most at the top, least at the bottom. Okay. So we're starting here with KBr. That's our potassium bromide. You may say, how do we know the formula of this? Well, potassium is in group 1 of the periodic table, so it forms a 1 positive ion. Okay. Bromine, all the halogens are in group 7. They form a 1 negative ion. Every halogen forms a 1 negative ion. So those charges on those ions are balanced. So the formula has to be KBr. So we're reacting with fluorine, I said. So I'm going to say that's the fluorine molecule. It's F2. All the halogens, when in their elemental state, form these diatomic molecules. In other words, it will have a little 2 at the bottom. Okay, so the most reactive halogen takes the cation. Now, so the most reactive halogen here is the one highest up the group, in this case fluorine, that's the most. The least is the one that's further down, the bromine in this case, and the cation is the potassium or the metal that they are fighting over. So the most reactive halogen takes the cation. So we're going to end up with potassium fluoride, and that leaves the bromine on its own. And then that equation will need balancing again. One potassium there, one bromine there, two bromines there, so we need to put a 2 before this one, and it carries on. Your equation will need balancing. That's a displacement reaction. Methane burning in plenty of oxygen, well, that's CH4. CH4 is methane. It's burning in plenty of oxygen, so we're going to react that with O2. Now the products of complete combustion, because it's plenty of oxygen, so plenty of oxygen means complete combustion, are carbon dioxide and water. Okay, next one down is methane burning in limited oxygen. That's incomplete combustion. So this is year 11 work. We've just done it on oil. This is incomplete combustion. The products of incomplete combustion are carbon monoxide, which is a colourless, odourless, toxic gas. You breathe it in, it binds to hemoglobin. So your bloodstream can't carry oxygen and carbon dioxide around it. It binds to hemoglobin, doesn't let go. So it's toxic, it kills people. And the other one is carbon solid or soot. That's a particulate. You breathe that and it can lead to long-term chronic breathing issues. So incomplete combustion is a problem. They are the products. Heating and pressurizing ethene, well, this is polymerization. Okay, now we went through that. I briefly put a video, an equation for that one on homework 8. So if you want to have a quick look at homework 8, I did outline that equation there. So have a quick look at that video. Heating copper oxide with carbon. Okay, this is year 10 revision. We did extracting metals from their ores. Okay, so displacement reaction again. Okay, so we had a reactivity series of metals, and we had the likes of aluminium at the top of it. And then we put carbon in there. Now carbon is a non-metal. Okay, but then we put less reactive metals like iron and copper, and maybe something like gold at the bottom. So most reactive at the top, least reactive at the bottom. Carbon fits into that reactivity series. Now metals generally, like aluminium, iron and copper, when they're found in the ground, are found as ores, which are oxides. They're powdery substances, they're not very strong, they're pretty useless to be honest. However, if we can chemically remove the oxygen, okay, so the copper oxide there, well, I'm going to do mine with iron. I'll do iron oxide. Okay, I'll give you the formula of copper oxide. The formula of copper oxide is CuO. I probably should have given you that. Iron oxide there, and if we react that with carbon, it's a displacement reaction. The carbon is more reactive than iron, so it takes the oxygen. It's going to make carbon dioxide and leave iron on its own. Okay, you're doing copper, I've done for iron. Again, balancing this equation, 2 irons here, so I'm going to need 2 irons there. I've got 3 oxygens on the left, and I've got 2 oxygens on the right. So that's never going to work, is it? 3 and 2. Until we find the first common multiple. The first common multiple of 3 and 2 is 6, so we're going to need 6 oxygens on the left and the right. So to get 6, I need to put a 2 before that. 2 times 2 irons, that changes that to 4 irons on that side now. And we needed 6 oxygens here, so I need to put a 3 before that. 3 times 2 is 6. 1 carbon here, 3 carbons here, put a 3 there. Again, that's not the answer to your question. You need to do it with copper oxide and carbon. The formula of copper oxide is CuO. I will try and add that to your book before it gets printed. Next one, electrolysis. Again, this was displacement here. Next one, electrolysis, passing a direct current through water. Okay, electrolysis breaks apart compounds. Okay, so this is water when it will split into hydrogen and oxygen. Okay. Now the way that works is water can ionize into hydrogen ions and hydroxide ions. So we need, first off, we need to deal a half equation for the hydrogen ion. The hydrogen ion in water turns into hydrogen, like so. Yes, and the hydroxide ion, that's a little bit more complicated, that turns into oxygen, which we know, but it also makes some more water. Okay, now we need to balance both of these equations in terms of electrons. Okay, this has got a positive charge. Now an element is always neutral. So we have to deal in electrons to turn that into something neutral. So that is going to need to gain an electron. Now, before you start writing that out and thinking you have nailed this, okay, you haven't, because it's not balanced. Look, 2 hydrogen atoms on this side, only 1 hydrogen ion on this side. So you're going to need to balance the hydrogen ions by increasing them. And that's also going to need more than 1 electron, isn't it? So you need to balance the hydrogen ions and balance the electrons. Do that, please. Likewise, down here, this has got a negative charge. This ion has got a negative charge. These products are neutral. Okay, so how does the hydroxide ion become neutral? It loses electrons. So there's going to be electrons on this side. Now that equation also is not balanced. My advice to you is balance the oxygens first, and then balance the hydrogens, and then balance the electrons. So those two need balancing. So this is obviously, that was obviously electrolysis. Next one, passing a long chain hydrocarbon over a hot porous catalyst. Okay, this is cracking. We're cracking long chain hydrocarbons. So I'll just give you one example. I'm going to say take C12. You need to think of a different example, maybe C10, just as an idea. C10H26. Okay, when you take that long chain hydrocarbon and heat it over a catalyst, it breaks apart and decomposes. So there's no other reactants. And let's just say it makes a C2H4 molecule, that's the alkene. And then we just need to take those two away from this. So that's going to be C10, because 12 minus 2 is 10. 26 is going to minus 4, it's going to be 22H22. Okay, do get a formulae of an alkene right. Don't just make that up, obviously. That's just an example of cracking. And the last one here, the half equation for the reaction. At the anode, when a solution containing sulfate ions is electrolyzed. Okay, so the anode is the positive electrode. Okay, and the sulfate ions are going to, let's just draw this out here. Let's just draw that out. So here's our negative electrode. So if this is a solution containing sulfate ions, SO4 2 minus ions, it's a solution, it's containing the sulfate ions, and of course it also contains hydroxide ions, OH minus ions. It contains 2 negative ions. You may say, where does the hydroxide ions come from? They come from water. Water, when it dissolves things, ionizes into hydrogen ions and hydroxide ions. Okay? So yes, there's hydrogen ions there, but we're only interested in the anode, the positive electrode, I should say. The anode is the positive electrode. So these negative ions are going to go towards that anode, that positive electrode. Now, only one of those can be given off. So this question is about learning the rules. Now, the rule is very simple, okay? If these anions are fluoride, chloride, bromide, or iodide, the halogen is produced. So say we were starting with sodium chloride solution, we'd have hydroxide ions and chloride ions, you'd get chlorine given off. Okay? If it was sodium bromide solution, we were starting bromide ions, we'd get bromine given off. If we were starting sodium fluoride ions, we get fluorine given off. Okay, we're not starting with a halogen, we're starting with sulfate. And because we don't start with a halogen, it is the hydroxide that wins. If it's the hydroxide that wins, we've already done that equation, it's here. That's the equation. Okay, it needs balancing, of course. Again, that's electrolysis. All right, some calculations to finish off. It's quite difficult homework. Concentration calculations. What is the concentration in grams per decimeter cubed? Well, I'm not going to do this one. Let's say we start with 20 grams and maybe 100 centimeter cubed of water, okay? 20 grams of sodium hydroxide is dissolved in 100 centimeter cubed of water. What is its concentration? Okay, well, this here is the clue. This is our formula. That little minus there means per. So this unit of concentration is grams per decimeter cubed. Now, the mathematical symbol divide is per. So you could write it out like that. Grams per decimeter cubed. And there's our formula. Grams, 20 grams divided by per decimeter cubed. 100 centimeter cubed. Now, of course, we need to put this into decimeter cubed. So to put a centimeter cubed into a decimeter cubed, you have to divide by 1,000. So that now tells you it's 0.1 decimeter cubed. Okay, so first thing to do, put the centimeter cubed of the water into decimeter cubed. You do that by dividing by 1,000. So 20 divided by 0.1. And that will be your answer. Stick it into a calculator if you want to stick it into a calculator, or do it in your head if you want to do it in your head. But if you do it in your head, my advice would be always, my calculator's giving up the ghost. All right, found it in the calculator. Okay, so let's put that into a calculator. 20 divided by 0.1, so we've got 20 divided by 0.1 equals 200. So our answer there is 200 grams per decimetre cubed. Now obviously that's not your answer to this question because I changed the numbers. But basically, grams per decimetre cubed, grams divided by decimetre cubed. Turn a centimetre cubed into a decimetre cubed by dividing by 1,000. Next one, calculate how many molecules are present in 5 moles of carbon monoxide. Okay, again, I often liken these questions to, you know, if I've got three dozen eggs, how many eggs do I have? Well, to do that, you would have to do the constant, which is the dozen. Okay, the constant, which is the dozen. And you'd have to multiply it by the number, wouldn't you? The number of dozen, the number. We have number of dozen, we have number of moles. Okay, so if we've got, you know, how many eggs if we've got 3 dozen, that's the constant 12 times the number of dozen, 3 times 12 is 36. Well, this is all we're going to do here. Let's just say I've got 3 moles of carbon monoxide. I would do my constant, which is here, 6.02 times 10 to the 23 multiplied by 3. You're obviously going to multiply it by 5, aren't you? When you do yours. Now, just be careful putting this into the calculator. This is where you're going to go wrong, if anywhere. We need to put this number, 6.02 times 10 to the 23, into the calculator. Okay, so let's run through this quickly. We need to do 6.02. Now, this is not a multiply here. That is not a multiply. You need to use that button times 10 to the x. On some people's calculators, it's called EXP. If you're using an iPhone, don't. It's actually called EE on an iPhone. The reason I say don't use an iPhone is you can't use an iPhone in an exam. Okay, so don't press multiply, press times 10 to the x. Okay, and then we need to press 23. Then it's multiply, for this multiply here. Multiply 3, and if you look at the screen, that's what we've got in there now. Okay, so that is the big multiply, that's the times 10 to the x. Okay, it should look like that. Then hit equals, and you get an answer down the bottom, 1.806 times 10 to the 24 equals 1.806 times 10 to the 24. That is not the answer to your homework because I changed 5 to a 3. You'll have to do it with 5. All right, good luck.